Okay, let's unpack this. Have you ever wondered what happens to text all those words and sentences, the very fabric of human communication, before a large language model or even just a simple translation tool can actually understand it?
Hmm.
It's a bit like preparing ingredients before you cook something complex, right? You can't just throw a whole carrot, skin and all, into a blender and expect smooth soup.
Right, you got to prep it first, peel it, chop it.
Exactly. You need to peel it, chop it, maybe even blanch it. Today, we're diving into that crucial, often unseen first step in natural language processing.
Tokenization.
Ah, yes, tokenization. It's the unsung hero that meticulously turns raw, messy human language into something machines can actually think with and learn from.
And what's truly fascinating here, I think, is how this seemingly simple process, just breaking down text,
Yeah,
has evolved. It's become this complex, vital art form, really.
an art form.
Yeah.
Interesting.
Yeah, and it directly impacts the capabilities, the efficiency, and ultimately the intelligence of the most advanced AI models we see today. We'll explore the various methods, from the, well, surprisingly basic, to the incredibly sophisticated,
Okay.
understanding their strengths, their weaknesses, and how these choices shape the very fabric of machine understanding itself.
So, our mission for you today is to cut through the jargon, bypass the overly academic stuff, and get right to the core of why tokenization matters so profoundly, especially now in this era of gigantic AI models that seem to understand everything. We're drawing from a diverse stack of sources here, everything from deep dives into the history of byte pair encoding on Wikipedia to cutting edge academic papers on tokenization for complex languages like Hindi.
Right, some really specific stuff.
Yeah, and even explorations into how this fundamental step makes the powerful transformer architecture truly excel. By the end of this deep dive, you'll have a crystal clear, well-informed picture of this foundational concept that underpins so much of modern AI.
That's the goal.
So let's start at the very beginning. What is tokenization at its most basic level? Why can't a machine just read text like we do?
Okay, yeah, good question. At its heart, tokenization is the foundational process of breaking down raw, continuous text.
Which to a computer is just a jumble of letters.
Exactly, just a
Yeah.
long string of characters. Tokenization breaks it down into smaller, discrete, and meaningful units. These units are what we call tokens.
Tokens, okay.
Think of it like a long block of unformed clay, right? Tokenization is the process of precisely carving that clay into distinct, usable bricks.
Ah, like building blocks.
Precisely, each with a purpose. And these bricks can vary in size and complexity. They might be entire words, smaller subword units like prefixes or suffixes, or even individual characters sometimes.
So different sizes of bricks depending on the job?
Kind of, yeah.
Yeah.
It's the essential first step that takes human-readable language and transforms it into a structured numerical format that machine learning models can actually process, analyze, and learn from.
So it's not just about arbitrarily chopping up text, right? It feels like there's a real art to getting these divisions right. But why is it so absolutely critical? Couldn't models just figure out words on their own?
That's a great question, and it really gets to the heart of it. You'd think an AI could just read a string of characters and make sense of it, but honestly, without tokenization, you're just feeding a jumbled mess to the algorithm.
Right. Garbage in, garbage out.
Pretty much.
Uh,
Its crucial importance lies in several areas. First, it's an absolutely fundamental pre-processing step for almost all natural language processing tasks, period.
okay. Like what kind of tasks?
Well, whether you're building a system for sentiment analysis, understanding emotional tone, or a question answering system to extract specific information,
Or chatbots.
chatbots, machine translation tools,
Yeah.
tokenization is the very first hurdle you need to clear. Imagine trying to analyze the sentiment of, I don't dislike it. If the model just saw, I don't dislike it, it would be lost. But if it sees I don't dislike it, it can then begin to understand the individual meanings and how they combine.
So the core idea is taking this free-flowing, messy text and giving it the structure an algorithm needs.
That's exactly it. Raw text, as we write and read it, is fundamentally unstructured. It just flows. Tokenization acts as the linguistic architect, if you will.
I like that analogy.
It converts this raw, unstructured text into a highly structured numerical format that machine learning models can then process and learn from effectively. It provides the necessary structure, the granularity for algorithms to perform their analyses efficiently.
So it's not just splitting, it's preparing the data.
Exactly. It's preparing data in a way that allows powerful algorithms to efficiently process and analyze the linguistic patterns within, extracting those nuggets of meaning from the vast ocean of words. Without it, the algorithms simply can't do their job. They lack the discrete units to operate on.
Can you give us some simple, tangible examples just to really illustrate what these tokens look like in practice?
Absolutely. Let's take a couple of basic examples to make it concrete. The simplest form is maybe sentence tokenization,
Okay.
where you take a larger block of text, like a paragraph,
Hmm.
and break it down into individual sentences. That's super useful for understanding the flow of ideas, for summarizing, or just making sure later steps work on complete thoughts.
Right, dealing with one thought at a time.
Exactly.
Right.
Then there's word tokenization, which is probably the most common and intuitive one. Here, you break a sentence into its individual words.
Okay.
For instance, take the sentence, "Hello, world." A common word tokenization might yield 4 distinct tokens. Hello, see us, world, and snan.
Ah, so the punctuation becomes its own token too, not just hello and world.
That's right. Notice how punctuation marks like the comma and the exclamation point are often treated as their own separate tokens. That's because they carry meaning, right? Semantic or grammatical meaning a pause, a question, an exclamation.
Things the model needs to understand.
Precisely. The model needs to understand and incorporate that into its processing. If the comma were just glued to hello, the model might misinterpret hello as a totally different word than hello without the comma.
That makes sense. And what about the most basic method, the one people might have bumped into maybe without even realizing it, like in basic coding?
You're probably thinking of white space tokenization.
Sounds about right.
It's the simplest, most intuitive approach. You just split the text based on spaces.
Yeah.
If you've ever used Python's split function on a string,
Yeah, I've done that.
then you've essentially performed white space tokenization. You just tell it, break here,
Yeah.
wherever there's a space.
Seems easy enough, but I guess it has limits.
Oh, definitely. While it's straightforward and easy to implement, it's very limited. As we just saw with hello, world, it doesn't handle punctuation effectively. The comma and exclamation mark would just stay attached to the words.
Right, you'd get hello and world.
Exactly. And it certainly struggles with more complex linguistic structures. Think about contractions like don't.
No.
That would become maybe dawn and tea.
Oh, yeah, that's not helpful.
Not at all. Or hyphenated words like well-being that becomes well and being. Or even proper nouns that contain spaces like New York.
Ah, New and York. Doesn't quite capture it.
No. It's a good starting point for understanding the concept, but it quickly reveals its severe limitations when you're dealing with the real nuances and complexities of natural language. So yeah, while simple splitting worked okay for really early systems, it quickly became clear that language was just far too nuanced for such a blunt instrument.
Right.
As natural language processing evolved, especially when we moved towards statistical methods and then machine learning methods, we absolutely needed more sophisticated approaches, things that went beyond just whole words. This led to techniques that could handle language with a far greater degree of intelligence.
I can imagine. Just splitting by spaces seems way too basic for complex understanding. What were some of those early innovations then that moved us beyond simple white space?
Well, beyond just splitting on white space, early innovations introduced things like n-gram-based methods.
Grams, like sequences of words.
Yeah, exactly. Sequences of n items could be characters or words, analyzing those to find common patterns rather than just isolated units. Then there were rule-based systems.
Like grammatical rules.
Yeah, applying predefined linguistic rules.
Yeah.
Maybe recognizing prefixes, suffixes, specific punctuation patterns to figure out the boundaries, and even techniques using finite state automata.
Okay, that sounds more complex.
They're abstract machines, basically designed to recognize patterns and sequences. They provide a powerful framework for parsing text based on pre-programmed states and transitions.
So getting smarter about how to chop up the text.
Definitely. These techniques allowed for a more intelligent handling of text, moving beyond simple character boundaries to consider sequences or applying linguistic rules. These were crucial steps, but the real game changer came with deep learning.
Ah, deep learning. That's where things really took off in AI, right? Especially
Yeah.
with large language models. So how did deep learning push for new, more refined tokenization methods? This led to subword units, you said.
Precisely. The rise of deep learning models, especially these massive language models like the transformers we'll talk about, really highlighted the urgent need for even more refined tokenization. Traditional whole word tokenization just faced too many big challenges when you try to scale up to these advanced architectures and the sheer amount of diverse text data they eat.
Okay.
This is exactly where subword tokenization emerged as this powerful, elegant, almost indispensable technique. Subword units became essential for overcoming a really persistent and nagging problem in NLP. Out of vocabulary words, OV words.
Oh, V words, that sounds like words the model just flat out doesn't know. Like a linguistic black hole for the AI.
Yeah. You've got it precisely. OV words are terms that a model hasn't encountered during its training phase. They're not in its predefined vocabulary.
And when it sees one,
When a model encounters an OOV word, it literally doesn't know what to do with it. It can't assign an appropriate numerical representation. It often just treats it as a generic, unknown token.
which obviously isn't good for understanding.
Not at all.
Yeah.
It drastically reduces its understanding, its ability to generate coherent responses, its overall performance. The causes are many. Maybe the model's vocabulary size was just too limited.
But the training data wasn't broad enough.
Could be. Or they could be genuinely rare or entirely new words. Think about emerging slang, highly specialized technical jargon. Specific proper nouns that just weren't in the training set a new company name, a new scientific term, a trending hashtag.
Misspellings too, I guess.
Misspellings, variations of words, yeah, another common culprit. And in some languages, the sheer number of possible word forms makes OV words a constant headache.
So if a model was trained mostly on, say, formal English, and then suddenly sees a word like riz or some super technical term like photovoltaic, it just hits a wall. Can't interpret it.
Precisely. If a model trained primarily on academic paper suddenly encounters a brand new slang word that just popped up, or a really specific niche technical term from a field it wasn't trained on extensively, it would classify it as OOV.
And that limits the model quite a bit in the real world.
Significantly. This inability to process unseen words limits its robustness, its versatility, its real-world applicability in dynamic language environments. And this issue is even more pronounced. It becomes a monumental challenge in what we call morphologically rich languages.
Morphologically rich languages. Okay, that sounds like languages where words change their form a lot depending on their role in a sentence. What kind of languages are we talking about, and how do subwords help tackle that specific hurdle?
Excellent point. Languages like Hindi, Finnish, Turkish, German, Hungarian are prime examples. In these languages, words can change their form significantly. You add numerous prefixes, suffixes, inflections to a root word.
To show tense, number, gender, all that stuff.
Exactly. Tense, number, gender, case, and more, all packed into a single word. In English, we might have walk, walked, walking. Pretty simple. But in a morphologically rich language, a single root word can have dozens, maybe hundreds of variations.
Wow.
And each one would be considered a distinct word by a traditional tokenizer. If you relied on whole word tokenization for a language like that, your vocabulary would just explode. It'd become impossibly large, hard to manage.
And you'd still get OOV words constant.
Exactly, because every new inflection or compound word would be considered a new word it hasn't seen.
So how do subwords rescue us here?
Subword tokenization comes to the rescue by breaking these complex words down into their meaningful components, the root forms, the common affixes.
Aha, the building blocks again.
Right. Imagine the sentence in Hindi, for example, like I portrayed constitute kumparo kotio parba karakaru. Teba karo sajo apok tikaroba agawaba haba karabolo couple boa. Lo pokapaku. Punka hyper khatis yaar postis to khalli. Dude, you band is bachana ke sana to yoga to ava. Kam karam ko next se jamara. Which means this search also provides complete information on the development of feathers.
Okay.
A traditional word tokenizer might struggle with all the inflections and compounds, lots of unknown tokens. But a subword tokenizer could segment it into units that represent the core meanings, even if they aren't full words. Like,
Yeah. I can see the underscores breaking it up. Like, tree from a blinking
Exactly. It splits the words into mini allowing the model to understand the building blocks rather than treating the whole inflected form as unknown. Similarly, in German, a crazy long compound word like Donau, Dampfschaft,
Laughs. Yeah, Danube Steamship Company. It could be broken down into Donau, Dampf, Schiff, Fahrtsgesellschaft. Each part carries meaning the model can combine.
So it's about finding that sweet spot. Not characters, because that's too granular, but not full words either, because of OOV. It's units that still carry linguistic meaning.
Exactly. Subword units achieve a crucial balancing act. They're a midpoint between character-by-character processing, which loses too much linguistic context, makes sequences really long, and makes it hard for models to learn meaningful patterns.
Right.
And word-by-word processing, which suffers heavily from OOV issues and needs huge, inefficient vocabularies.
So subwords are the Goldilocks solution.
Kind of, yeah. By breaking words into meaningful subwords, often aligning with morphemes, these techniques drastically alleviate the OOV problem. This lets models work with a much smaller, more manageable vocabulary.
Which is more efficient.
Way more efficient. And they can still process and understand virtually any word, even ones they haven't seen before, just by reconstructing them from known subword units. This efficiency and robustness are paramount for building these large, versatile, adaptable AI models, enabling them to understand a much wider range of human language.
Okay, so when we talk about these subword approaches, three names keep popping up: BPE, word piece, and sentence piece. These seem to be the workhorses behind so many of the powerful AI models we use. Let's break down how these influential methods actually work.
Indeed, these three really form the backbone of subword tokenization in modern NLP. Each has its unique approach, born from different design philosophies and optimized for different needs.
Let's start with byte pair encoding, BPE. It has a fascinating history, you mentioned. Originally for data compression, how did it jump from saving disk space to helping AI understand language?
BPE's origin story is really cool. First described back in '94 by Philip Gage. And yeah, initially it wasn't even for language processing. It was a simple but effective algorithm for data compression, known as BPE, or diagram coding.
Diagram coding, like pairs of symbols.
Exactly. The original mechanism was clever for compression.
Yeah.
It would find the most frequent pair of adjacent bytes in a dataset.
Bytes, not characters.
Bytes, yeah. And it would replace that pair with a new single byte that wasn't already in the dataset. To decompress, you just needed a lookup table to reverse the replacements. It was all about finding redundancy and shortening things.
Okay, literally saving space by finding common byte pairs. How did that idea, which seems pretty far removed from language meaning, get adapted for AI and become so powerful?
Right, so the modified version of BPE, the one we use for large language model tokenizers today, applies that same core principle. But instead of bytes, it's building tokens that match varying amounts of the source text.
Okay.
It starts with a vocabulary made up of every individual unique character found in your training data. Think of these as your initial tiny tokens, every letter, digit, punctuation mark.
The absolute basics.
Yes. Then it iteratively searches for the most frequent pair of adjacent tokens within the entire text corpus.
Finds the most common neighbor pair.
Exactly. Once found, that frequent pair gets merged into a new, longer n-gram. This creates a new, larger token.
Okay.
And all instances of the original pair are then replaced by this new token throughout the text. This greedy process repeats, merge after merge, building up longer and longer subword units from the most common adjacent pairs until you hit a predefined vocabulary size.
So it's greedy, always merging the most frequent pair.
That's a key characteristic, yes. It keeps building up.
So it's like building words from common letter combinations. If I have a simple example, maybe the string ababa, how would BPE handle that?
That's a great way to visualize it. With ABBA, the algorithm would first see that I is the most frequent adjacent pair.
Okay.
BPE merges I into a new token. Let's call it Z. Now your string is ZBOB ZIA.
Right.
Then it scans again. Maybe AB is now the most frequent pair. It merges AB into, say, Y. Your string becomes ZYYZ.
I see. It keeps iterating.
It keeps merging until it hits a preset limit, like a maximum vocabulary size you set for your model. And the beauty is its flexibility. Even new words that weren't in the original training data can almost always be reconstructed from the final subword tokens and the initial characters.
So it generalizes pretty well.
Very well. Allows for excellent generalization.
And I've heard about byte level BPE. Is that just taking the same idea even further down to the byte level? That seems almost too granular. What's the benefit there?
Exactly. Byte-level BPE is a critical variant. It takes the text, first converts it into its UTF-8 byte representation. Then it treats that stream of bytes as the input for the BPE algorithm.
Why do that?
It might seem overly granular, but this approach guarantees that any text encoded in UTF-8 can be tokenized. That's crucial for handling diverse global languages with vast character sets. Think Chinese, Japanese, Korean, even emojis.
Ah, so it avoids problems with unknown characters.
Exactly. No out-of-vocabulary character problems. Because every possible character is broken down into its fundamental bytes, the model never encounters an unknown character. This method's been widely adopted in major models. Roberta, BART, DeBerta, even GPT-2 used it.
Wow. Okay, so it's very robust.
Incredibly robust. And it's not just for spoken languages. BPE has even been extended to applications in sign language recently, which really shows its versatility.
Fascinating. Okay, next up, word piece. Famously used in Google's BERT models, How does word peace differ from BPE? Is it just a variation, or is there a more fundamental difference in philosophy?
Word peace is definitely a staple, yeah, primarily known for its use in BERT and similar transformer models. It also aims to create subword units, but its core principle for merging pairs is significantly different from BPE's simple frequency count.
Okay.
Word peace also uses a greedy longest match first strategy, often called maximum matching or max match, during the actual tokenization step, the inference phase.
Yeah.
But how it builds its vocabulary is different.
How so?
Instead of just picking the most frequent pair, word peace's merge decision depends on a specific count metric. This metric is calculated as the frequency of the pair, xy, divided by the frequency of x times the frequency of y.
Whoa, okay. Frequency of the pair divided by the product of their individual frequencies. That's not just about commonality. What's the subtle genius there? Why that specific formula?
That's the subtle genius. It's designed to identify merges that add the most new information, or you could say predictive power, to the model.
Ah, information game.
Exactly. It prioritizes pairs that are highly associated with each other, more so than you'd expect just from their individual occurrences. This metric basically measures how much more likely X and Y are to appear together than if they were just randomly placed.
Interesting.
The pair with the highest value from this calculation gets chosen for the merge, added to the vocabulary, and then conceptually, the language model is retrained with this new subword unit. This metric favors merges that create more meaningful or informative subwords, not just the most common character combinations.
So it helps make the text more predictable for the model.
Yes, it helps reduce the overall entropy of the text, making it more predictable, which is a powerful optimization for the model's learning process.
That's a really clever distinction. And I recall seeing some specific formatting with word peace tokens. Sometimes they have a hashtag prefix. What's that about? Does it tell the model something specific?
Yes, good catch. That's a key identifier. Subword tokens generated by WordPeace often start with hashtag tag. This is a convention, a signal to the model, indicating that this token isn't a whole word on its own, but part of a larger word.
Like a continuation marker?
Kind of. For example, simultaneously might be tokenized as simult, hashtag aneously. Or transformers could become transform, hashtag acocators. This marker helps the model understand these are fragments combining to form a complete lexical unit.
Guiding how it reassembles the meaning.
Exactly. It helps understand the internal structure and dependencies within words.
Okay, and finally, sentence piece. What's its niche? Its name suggests it deals with whole sentences, but is that right?
Sentence piece is another widely adopted subword method, and it stands out for its versatility, especially in multilingual contexts and for languages that don't have clear word boundaries.
Like Japanese or Chinese.
Exactly. It's often used in models designed to handle many languages at once, like MBERT and XLMR, and it's been found particularly effective for Indian languages, too. Its unique strength is its flexibility because it's essentially language agnostic.
Language agnostic. How?
Unlike BPE and WordPeace, which usually assume white space already marks word boundaries, sentence piece works directly on the raw text stream without any pre-tokenization.
So it doesn't even assume what a word is. It just looks at the raw string of characters. How does that make it better for multilingualism?
Exactly. Its ability to build vocabulary directly from raw text, including special characters and even spaces, makes it incredibly robust. It can treat spaces as just another character to potentially include in a token or learn to handle them intelligently.
So it can handle scripts without spaces naturally.
Yes. This means it can build a shared vocabulary across different scripts and languages, even if they have vastly different writing systems or don't use spaces. A single sentence piece model can train on a mix of English, Japanese, and Hindi text, learning subword units meaningful across all of them.
That's powerful for multilingual models.
It really is. It allows for a truly unified approach, improving cross-lingual transfer learning and boosting performance, especially for lower resource languages that might lack massive datasets. Its raw text approach ensures consistency and handles varied linguistic structures seamlessly. Okay, so if tokenization is that meticulously crafted foundation, then the transformer architecture is definitely the towering, innovative skyscraper of modern AI.
Good analogy.
And you truly can't have one without the other. Let's connect these critical pieces now and understand why tokenization isn't just some prep step, but an intrinsic part of how transformers achieve their remarkable capabilities.
The transformer architecture. Yeah, that's the groundbreaking innovation behind pretty much every large language model we interact with today, right? From ChatGPT to advanced translation tools, it really felt like a paradigm shift.
Absolutely. The transformer architecture, first proposed in that seminal 2017 paper, Attention is All You Need, truly revolutionized NLP. Before transformers, The dominant architectures were things like recurrent neural networks, RNNs, and their cousins LSTMs.
Right, I remember LSTMs.
They were powerful, but they processed text sequentially, word by word. That made them incredibly slow for long sequences and hard to parallelize during training.
The infamous vanishing gradient problem too, right?
That too. And the sequential nature created a bottleneck where information from early in a sequence could get lost by the time it reached the end. Transformers changed everything with their multi-head attention mechanism, and crucially, by completely ditching those recurrent units.
Attention is all you need literally got rid of recurrence.
Exactly. Instead of processing word by word, Transformers could process all tokens in a sequence simultaneously, in parallel. This meant significantly faster training times, enabling much larger, more powerful models that could finally grasp very long-range dependencies in text.
And now they're everywhere.
They're the undisputed backbone of LLMs, like GPT-2, 3, 4, BERT, you name it, powering everything from machine translation to code generation. Complex reasoning.
So how does tokenization fit into this transformer picture? Is it literally the very first thing that happens when text goes in?
Yes, that's exactly right. Every transformer model, without exception, starts its pipeline with a tokenizer. It's the indispensable first step.
Okay.
The tokenizer's job is to convert that human-readable text words, sentences, into numerical representations. These are the tokens we've been discussing, basically unique numerical IDs for the subword units in the model's vocabulary.
Got it. From words to numbers.
Without this initial conversion, the complex math inside the transformer just wouldn't have anything understandable to work with. It'd be like trying to do algebra with letters instead of numbers.
And once the text is broken into tokens and given IDs, what happens next before the main transformer layers? Do they just get fed straight in?
Not quite. After tokenization, these numerical tokens go into what's called an embedding layer. This layer is crucial.
Why? What does it do?
It converts each token's ID into a dense numerical vector, an embedding. These embeddings are powerful because they capture semantic meaning. Tokens with similar meanings or used in similar contexts will end up with similar vector representations in this high-dimensional space.
So cat would be near kitten but far from car.
Exactly like that.
Uh-huh.
But language isn't just about word meanings. Order matters hugely. So to preserve this sequence information, positional encoding is also added to these embeddings.
Right. Because transformers process in parallel, they need to know the order explicitly.
Precisely. Unlike RNNs that process sequentially, transformers look at everything at once, so they need this extra signal to understand word order. Dog bites man versus man bites dog.
Makes perfect sense. So once you have these token embeddings, now rich with meaning and position info, what happens inside the actual transformer layers?
Within the transformer, these vector representations undergo repeated transformations across multiple transformer layers. Each layer refines the representation, extracting deeper linguistic information and context. A core mechanism here is self-attention.
Self-attention. Okay, what's that?
Imagine each token in the sequence, looking at every other token in that same sequence. It's trying to figure out how relevant each token is to its own meaning in this specific context.
Okay.
So if the token is bank, self-attention might weigh whether the word river or the word money elsewhere in the sentence is more relevant to understanding this bank. And this happens in parallel for all tokens simultaneously.
Wow, okay. That sounds computationally intensive, but powerful for context.
It is. And that parallel nature is key to the transformer's efficiency and ability to capture those long-range dependencies.
And then there's multi-head attention, which sounds like doing that attention process multiple times, but differently. Like looking at different things.
Precisely. Transformers don't just use one attention mechanism, they use multi-head attention. Multiple attention heads operate in parallel. Each head learns a different definition of relevance or a different type of relationship.
Like different specialists?
Kind of. One head might learn to focus on the very next word, good for local dependencies. Another might specialize in linking verbs to their direct objects, no matter how far apart they are.
Ah, like subject-verb agreement or something?
Or corference linking pronouns back to the nouns they refer to. This parallel processing with diverse perspectives makes the model incredibly powerful at capturing a wide range of complex linguistic relationships simultaneously.
Okay, so it builds up a really rich understanding.
Exactly. The outputs from these heads are then combined and processed further through feed-forward networks in each layer, building an increasingly sophisticated understanding.
So given all this complexity, how do the subword tokens specifically help transformers excel? They seem like such tiny pieces, but they must make a big difference.
They make a huge difference. Subword tokenization is a truly crucial enabler. First, And maybe most fundamentally, by breaking words into subwords, transformers handle rare or unseen words, those OOV words, much more gracefully.
Right, the OOV problem again.
If unbelievable isn't in the vocabulary, but unbelieve and able are, the model can still process and understand it by combining the meanings of its parts. It's like deciphering a new word using known prefixes and suffixes.
Instead of just giving up and marking it unknown.
Exactly, which is a massive leap forward compared to older methods that would just leave a gap in the model's understanding.
And this also helps keep the model's vocabulary size manageable, right? Which I imagine is a big deal computationally.
Absolutely. The subword approach means a significantly smaller vocabulary. Instead of storing every single word variation, all the plurals, tenses, inflections, the model just needs a finite set of common subword units.
Fewer things to learn, less memory needed.
Dramatically reduces computational overhead, memory requirements, the number of parameters the model needs to learn. This efficiency is precisely what makes training these truly massive language models on petabytes of data feasible without needing, planet-sized computers.
And what about contextualized embeddings? How do subwords play into that deeper, more nuanced understanding that makes models like BERT so impressive?
This is where it gets really interesting, showing this energy. Models like BERT and GPT don't just assign a fixed meaning to a word, they use contextualized embeddings.
Meaning the context changes the embedding.
Yes, the numerical representation, the meaning of a subword, and therefore the whole word, is dynamically influenced by its surrounding text. This allows for that rich understanding of nuance bank, meaning riverbank, or financial institution. For an OV word tokenized into multiple subwords, like simultaneously, becoming simult, #aneously, the embedding for the whole word can be derived in several ways.
How?
You might just take the embedding of the first subword token that often carries more weight in word piece. Or, a common strategy is to just average all the subword embeddings.
Simple average.
Yeah, effective for general tasks. Or, for things like translation or sentiment analysis, maybe a weighted average based on the attention scores from the transformer layers is even better. It lets the model focus on the most relevant bits for that specific context.
That's incredibly clever. It really shows how the model builds meaning piece by piece. And I've heard about a special token in BERT, the CLS token. What's its specific role in all this?
The CLS token, short for classification. It's a special token BERT inserts at the very beginning of every input sequence.
Always the first one.
Always. Its embedding is specifically designed, through the training process, to learn a summary representation of the entire sequence.
Like a condensed version of the whole input.
Exactly. This consolidated representation is then often used for sentence-level tasks, classifying sentiment of the whole sentence, determining if two sentences are related, maybe even summarization. It gives you a convenient single vector that encapsulates the holistic meaning.
The model's thought bubble for the whole sentence, you could say?
That's a great way to put it. Extremely useful for many downstream applications where you need one output for the whole input, not for each individual token.
Okay, let's zoom in on one of NLP's killer apps, machine translation. How does the choice of tokenization method directly affect whether a translation sounds natural, accurate, or just plain weird, like something a robot spat out?
That's a critical point because machine translation, MT, is a prime example where tokenization has a direct, measurable impact on quality. MT aims to automatically convert text or speech between languages, right? Breaking down those linguistic barriers.
The dream.
But without accurate, context-aware tokenization, the whole translation process just crumbles. It's absolutely essential for things like morphological analysis.
Understanding word parts again.
Yes, helping MT models distinguish prefixes, suffixes, root words. This ensures inflected words are translated precisely, not just treated as completely different, unknown terms. Crucial for accuracy, especially in those morphologically rich languages where word forms change constantly.
So even for older methods like statistical machine translation, SMT, tokenization was already making a difference. I kind of thought those were more about raw word-for-word probabilities.
Oh, it was making a substantial difference even then. SMT relies on statistical models trained on huge data sets to predict translations probabilistically. DPE tokenization played a vital role there by dividing words into subword units.
How did that help SMT?
It directly addressed a major challenge called data sparsity. If a phrase or a rare word only appears a few times as a whole unit in the training data, the SMT model struggles to learn reliable translation probabilities for it.
Not enough examples.
Exactly. But by breaking words into subwords, SMT models could learn probabilities for individual subword units that appeared much more frequently, even if the whole word was rare. This led to better, more robust representations for less common keywords, boosting accuracy and coverage.
So it helped handle a broader vocabulary effectively.
Precisely. By breaking words down, SMT could cope better.
And then, with the leap to neuro-machine translation, NMT, the transformer-based systems, how does tokenization's role change or deepen? Does it become even more tightly integrated?
With NMT, its role becomes even more integrated and sophisticated. NMT models use neural networks, typically transformers, to learn translation mappings directly, not just relying on statistical phrase tables.
Leading to more fluent translation.
Much more fluent and contextually accurate translations, thanks to their encoder-decoder architectures, which excel at capturing complex relationships. With NMT, BPE tokenization allows the model to learn from a much larger set of subword units, not just whole words.
Giving it more fine-grained input.
Exactly. It's not just about efficiency. It lets the model understand incredibly detailed linguistic patterns and nuances in both the source and target languages. Think about it. A typical transformer NMT model might have 6 encoders and 6 decoder layers, each with maybe 8 attention heads.
Lots of processing power.
Specifically designed to process these fine-grained subword tokens and build rich contextual representations. This allows them to translate complex sentence structures and idioms that SMT would totally mangle.
So BPE's subwords let these complex NMT models really grasp the intricacies and sound more natural. What about multilingual neural machine translation, MNMT? Translating many languages at once, that sounds like an even bigger tokenization challenge.
It is, and this is where BPE truly shines and becomes critical. MNMT models are designed to interpret and translate across numerous languages simultaneously, often using a single model.
One model for everything. Wow.
Yeah, it's a rapidly growing area. For MMMT, BPE is indispensable because it helps these models efficiently handle diverse multilingual datasets. Its flexibility in creating shared subword vocabularies allows MNMT models to perform across a wide range of language pairs.
Shared vocabulary is the key.
Absolutely. This shared subword vocabulary enables knowledge exchange across languages. The model might learn a subword like "un" from English and apply that understanding to a similar negative prefix in Spanish or German.
Transfer learning between languages.
Exactly. Enhancing translation quality for all involved languages, especially low-resource languages that might not have much training data on their own. By learning common subword representations that transcend specific languages, the model leverages similarities, leading to better overall performance and more robust translations. Okay, so it's all well and good to say one method is better than another, but in the rigorous world of AI, we need to quantify that, right? We can't just rely on intuition.
Need the numbers.
Exactly. There's an entire suite of sophisticated metrics developed specifically to evaluate machine translation quality. And these metrics, in turn, give us crucial insights into how effective the underlying tokenization methods really are.
So we can actually put a number on how good a translation is. That's fascinating, especially given how subtle language can be. What are some of these key evaluation metrics researchers use?
Indeed, we can. One of the most famous and widely used, almost a household name in NLP circles, is BLEU. BLEU stands for Bilingual Evaluation Understudy.
Okay, BLEU. How does it work?
BLEU basically evaluates the overlap of n-grams between the machine translation and one or more human reference translations.
N-grams, again, sequences of words.
Yeah, like finding if the machine translated the big dog, a 3-gram is the big dog, or maybe large dog, it checks how many phrases, short and slightly longer, the machine got exactly right compared to human versions.
Higher score is better.
Yes, scores range from 0 to 100. Higher BLEU generally means closer to human references. It's popular because it's simple and computationally efficient. But its limitation is it only looks at surface-level matches exact word sequences. It doesn't capture semantic meaning or fluency that well.
Right. Just checks if the same words were used in roughly the same order. What other metrics go beyond that? Maybe looking at how much work it takes to fix a bad translation.
For that, an important one is TR, the translation edit rate. T measures the number of edits needed.
Edits like insertions, deletions.
Exactly. Insertions, deletions, substitutions, or even shifts of words required to transform the machine translation into an exact match of a human reference.
So lower T is better, less fixing needed.
Precisely. Lower T scores mean higher quality because fewer edits are needed to make it perfect, often expressed as a percentage. It's a good indicator of post-editing effort, but it doesn't tell you why the edits were needed.
Okay, so BLEU for similarity, TER for effort. What about capturing meaning more deeply? Considering synonyms or different ways of saying the same thing.
For that, we have Meteor, metric for evaluation translation with explicit ordering. Meteor is seen as an improvement over BLEU because it goes beyond just direct word matches.
How does it do that?
It incorporates synonyms, partial matches, stemming reduced words to their root form, so walking and walked relate to walk, and it explicitly considers word order. It assigns different weights to different match types, trying to capture semantic similarity more accurately.
Sounds smarter than BLEU.
It often aligns more closely with human judgment of adequacy and fluency, but it still relies on fixed rules and external resources, like WordNet for synonyms, which can have limitations.
And for those morphologically rich languages we keep mentioning, like Hindi or Finnish, where words get complex, is there a metric suited for that?
Absolutely, that'd be CHRF, character n-gram F-score. Unlike BLEU or Meteor, which focus on words, CHRF analyzes character n-gram matches.
Looking at sequences of letters.
Yes, exactly. Focusing on subword similarity, it computes an F-score, balancing precision and recall for these character-level n-grams. This makes it highly sensitive to slight spelling or morphological variations.
So it's good for languages with lots of suffixes and prefixes?
Particularly well-suited for them, yeah.
Yeah.
Where subtle changes can alter meaning. But its focus on character similarity can sometimes penalize translations that rephrase things well at the sentence level, just because the character sequences are different.
Trade-offs. We also talked about how critical word order is. Dog bites man versus man bites dog. Is there a metric specifically for assessing that structural accuracy?
Yes, there is. RIBES, Rank-Based Intuitive Bilingual Evaluation Score. It's designed to assess quality with a strong focus on word order.
How?
It evaluates the connection of word positions in the source and translated sentences, checking if the structural accuracy, crucial for meaning, is maintained. It quantifies how well the translation preserves the relative ordering of words, important for languages where order is key.
Okay. And finally, you mentioned a newer neural-based metric, COMET, C-O-M-E-T. What makes it different from these others? Why is it cutting edge?
COMET, cross-lingual optimized metric for evaluation of translation. It's more recent and really advanced because it's neural-based. Instead of relying on n-gram overlap or character matches or fixed rules,
It uses AI itself.
essentially, yes, it leverages embeddings from pre-trained language models, which are sophisticated AI systems themselves. It uses a regression model trained to estimate human quality scores by analyzing source and target translations using these rich semantic embeddings.
So it learns what humans think is a good translation.
Exactly. It tries to capture much deeper semantic alignment across languages, recognizing subtle similarities and flaws that rule-based metrics might miss entirely. It's learning to think like a human judge, making it highly correlated with human judgments of quality.
That's a comprehensive toolkit, each metric looking at quality from a different angle. Were there any specific studies comparing these tokenization methods, BPE, word piece, sentence piece, using these metrics, maybe across diverse languages? That would really tie things together.
Indeed, there was a significant study on 11 Indian languages that did exactly that. Compared BPE, word piece, and sentence piece across SMT, NMT, and MNMT models. The results were quite revealing.
Oh, interesting. What were the key findings? Did one method just win out across the board, or was it more nuanced?
It was more nuanced, which is often the case in AI context really matters. The key finding was that there isn't a single best tokenizer for all situations. While sentence piece consistently produced better BLEU scores for most NMT and SMT language pairs in that study.
Okay, sentence piece looked good there.
It turned out that BPE tokenization actually performed better than the other techniques, specifically in the context of multilingual neural machine translation, MNMT models.
So BPE was better for the models translating many languages at once. Why would that be?
It highlights how the optimal method depends heavily on the MT architecture and the languages involved. For MNMT, BPE's ability to create that universal shared subword vocabulary, seemingly regardless of language or script, proved to be a decisive advantage in that study.
Enabling better knowledge transfer within that single multilingual model.
That seems to be the case. Sentence piece, while versatile, might have generated more subwords unique to each language in that context, making the shared representations less efficient for that specific MNMT architecture. BPE provided a more common ground.
Can you give an illustrative example from that study? Like for MNMT with BPE, which language pairs did best or worst?
Certainly. For MNMT, the study showed the English-Hindi ENAI model achieved the highest BLEU score using BPE tokenization. Significant given Hindi's morphology.
Okay. And the lowest?
In contrast, the English-Assamese ENAS model had the lowest BLEU score, even with BPE. The researchers suggested the main reason was likely a smaller training corpus available for Assamese compared to Hindi.
So data still matters hugely, even with the best tokenizer.
Absolutely critical.
Hmm.
It emphasizes that even with optimal tokenization, the quality and quantity of training data remain paramount. So yeah, the impact of tokenization is tangible, affecting fluency and accuracy, but it varies significantly based on language pair, model architecture, SMT, NMT, MNMT, and data. It's a delicate interplay.
Okay, shifting gears slightly. In the fast-paced world of AI, where milliseconds can mean millions of dollars or just a much better user experience, speed is everything. Even if tokenization is just that small initial step, it's foundational. Optimizing it must have massive downstream effects. So what are researchers doing to make this process even faster, more efficient, pushing the boundaries?
You've hit on a critical point. While tokenization might seem like just pre-processing, its efficiency has enormous implications. Because it's an absolute prerequisite for almost all NLP tasks, any speed improvement directly cuts the overall latency of AI inference, how fast the model responds.
Which matters a lot for real-time apps.
Hugely important for mobile NLP apps. Yeah. Real-time translation on your phone, on-device voice assistance, every millisecond counts for a smooth experience. Slow tokenization makes the whole thing feel sluggish.
And I can imagine for huge tech companies like Google operating at massive scale, even tiny efficiency gains add up to something enormous.
Absolutely. For services processing billions of search queries, indexing trillions of web pages daily for ranking, info retrieval, spam detection, faster tokenization means huge aggregate computational savings.
And less energy consumption, too.
Exactly. It's not just speed and cost. It has a significant environmental benefit through less power consumption. Optimizing this foundational step literally saves energy on a grand scale, reducing the carbon footprint of these massive AI operations. Low-level algorithms, high-level impact.
That's a powerful incentive. So what's one of the cutting-edge algorithms speeding things up, especially for word peace? I think I read about something called Lin-Max Match. How does that work?
Yes, Lin-Max Match is a prime example of this efficiency drive. Developed by Google researchers for single-word, word-piece tokenization. Its key innovation is achieving asymptotically optimal linear time complexity.
Okay, break that down. Linear time complexity.
It means the time it takes to tokenize grows in a straight line with the length of the text. ON, complexity. Double the text, roughly double the processing time. No unexpected slowdowns as input gets massive, crucial for large data sets and real-time stuff.
And that was a first for WordPieces max match strategy.
First time such optimality was proven for MaxMatch, yeah. And it achieves this without a vocabulary-specific factor that would slow it down as the vocabulary gets bigger.
How does it manage to be so efficient? Is it a totally new way of doing WordPiece?
It's an ingenious adaptation. Lin-Max Match is inspired by the classic Ojo-Karasik algorithm, which is great for finding many patterns quickly. Lin-Max Match builds a special, like a decision tree, for letters from its subword vocabulary. The clever part is adding failure links and failure pops to this tree. Think of them like smart shortcuts. If the algorithm is going down the tree and hits a dead end, the characters don't form a valid subword.
Instead of backing up slowly.
Exactly. Instead of backtracking wastefully, these links instantly guide it to the next most likely matching point. It's like having a map that shows the quickest recovery route, cutting down wasted effort.
Smart navigation.
Very. Now, the pre-computation to build this complex trie can be intensive, done offline, so it doesn't slow down the actual real-time tokenization.
So Lin-Max Match nails single-word tokenization efficiency. But what about whole sentences or texts with multiple words, punctuations, spaces? Does that need a different optimization?
That's where the end-to-end word piece, or E2E word piece tokenizer, comes in. It targets the entire input stream. Traditional word piece often does two steps. First, pre-tokenize into words using space punctuation, then tokenize each word into word pieces.
And it passes.
Right. E2E word piece revolutionizes this by combining those two steps into a single linear time pass.
Just one pass over the text. What are the practical benefits? Must be faster.
Dramatically higher efficiency, less overhead.
Yeah.
By combining steps, E2E word piece traverses the input only once. Fewer punctuation whitespace checks. Crucially, it avoids creating intermediate word objects in memory, a big source of slowdown.
And the real-world speed up.
Substantial. Experiments showed E2E word piece was around 8.2 times faster than Hugging Face tokenizers and 5.1 times faster than TensorFlow text on average for general text tokenization.
Wow, 5x to 8x faster. That's huge.
That kind of speed up is transformative for large-scale apps, web search, data analysis, and it helps smaller teams and researchers too, not just Google. More experiments, faster processing, more responsive apps.
That's incredible, democratizing faster AI. Are there other areas where researchers are speeding up the whole transformer model beyond just tokenization? It seems like every part is being optimized.
Absolutely. The drive for efficiency is relentless across the whole architecture. One exciting area is speculative decoding.
Speculative decoding sounds like guessing.
Kind of. It uses a smaller, faster model to generate speculative future tokens, a quick guess at the next few words.
Okay.
These guesses are then quickly verified by the larger, more accurate transformer model. If the guesses are correct, they're kept, speeding things up because the big model didn't have to generate them.
And if they're wrong,
Discarded and recomputed by the larger model. But the net effect is often a considerable speed up, especially for simpler text, like a smarter autocomplete for the AI's output.
predicting ahead, letting the big model just check the work. Clever. What else is helping speed things up?
Another area is multi-token prediction. Traditionally, a transformer makes one forward pass to predict the next single token. Multi-token prediction allows a single forward pass to generate a sequence of subsequent tokens.
Multiple tokens at once.
Yeah. You trade off a tiny bit of accuracy maybe, but gain significant speed as each extra token costs less computation than starting over. Useful where speed is paramount.
And I've heard about subquadratic transformers. What's the big deal there? Quadratic sounds like things get out of hand fast.
That's a crucial area for pushing context length limits. Standard attention in transformers has a memory cost that grows quadratically with input sequence length.
Meaning double the input length, quadruple the memory.
Exactly. Memory requirements explode quickly, limiting how much text a model can handle at once. That's why LLMs have context limits.
So subquadratic means breaking that barrier.
Yes. Researchers are developing new architectures, attention-free transformers, ones using random feature attention that reduce this cost dependency to linear instead of ON2.
Linear growth. Much more manageable.
Way more. This fundamental shift allows for much, much longer context windows. Models could potentially process entire books, long documents, extended conversations without running out of memory, vital for truly comprehensive language understanding.
So what does this all mean for you, our listener? Well, the next time you see a machine instantly translate a complex sentence or an LLM generate incredibly human-like text,
Sounding almost real.
yeah, you'll know it's not magic. It's not just throwing words at a supercomputer. It starts with the meticulous, often invisible work of tokenization. That critical first step, breaking language into units machines can grasp. And as we've seen, perfecting that step, and really every step in the AI pipeline, is this ongoing fascinating challenge driving innovation.
And it raises an important question, doesn't it? As models get even more sophisticated, understanding deeper nuance, generating highly contextual responses, how will tokenization keep evolving?
Good question. What's next?
Will we see even more morphologically aware systems, parsing word structure perfectly in any language, or maybe entirely new paradigms beyond subwords, pushing what AI can truly comprehend and create, maybe learning to generate language more organically, not just token by token?
Fascinating possibilities.
The journey from raw text to truly intelligent understanding is definitely far from over. And these foundational innovations like tokenization will keep shaping that future.
Join us next time on The Deep Dive as we continue to unravel the fascinating world beneath the surface of technology and knowledge.